Thanks very much. Can you hear me okay? How's the sound? Can everyone hear me okay? Great. So as Esther said, I'm Allison Kaptur. I work at Dropbox in San Francisco. I was previously a facilitator at the Recurse Center, which you may know by the name Hacker School. And these are some places that you can find me on the internet, GitHub and Twitter, and this is basically my handle anywhere on the internet. So today I'm going to talk about writing a Python interpreter in Python, particularly a CPython interpreter. The name of this project is Byterun. It was done primarily with Ned Batchelder. He did most of the Python 2 support. I came in to do Python 3 support and debugged a couple of interesting things. I've been working on this with Ned for about a year, and it's been a really interesting and educational experience, and I want to share some of that with all of you today. So before we get started, the word interpreter is used in a variety of different ways when people are talking about Python. Sometimes when someone says the interpreter, they mean the REPL, the interactive interpreter that you get when you type Python into the command line. Sometimes people say the Python interpreter to mean like all of Python, the whole process of executing code. Today we're going to talk about it in a more narrow sense. An interpreter, for our purposes, is the last step in the process of running a Python program. When Python executes your code, you can think of there being 4 stages. There's lexing and parsing, which is going from source code in files to an AST that the compiler knows what to do with. Then there's compiling, which is taking that AST and turning it into a code object the interpreter knows how to handle. And then there's interpreting, which is taking that code object and actually doing whatever it says. So Byterun is a Python interpreter in this sense. It takes compiled code objects and makes them run. You may be surprised to hear that compiling is a step in Python at all, since Python is famously an interpreted language in contrast with a compiled language like C or Rust. It turns out that this terminology is not as precise as it seems. And in fact, most interpreted languages, including Python, do involve a compilation step. So the reason why Python is called interpreted, even though it involves compilation, is that the compilation doesn't do a lot of work in Python, and the compiler knows very little. And by contrast, the interpreter does a lot more work, and the interpreter is responsible for a lot more. And the Python compiler has much less information about the program that is going to execute than a C compiler does. A Python interpreter is a virtual machine, which just means that it's software that emulates a physical computer. And this particular virtual machine is a stack machine, so it manipulates several stacks to perform its operations. This is in contrast with a register machine, which you could imagine. A virtual register machine is a little bit of a weird thing, but the idea there would be that you'd write to and read from various locations in memory. So instead of doing that, we're operating on a stack. And in particular, the Python interpreter is a bytecode interpreter. So its input is these instruction sets called bytecode. When you write Python, the lexer, parser, and compiler generate the bytecode. In addition to some extra parts that the interpreter needs to run. And the interpreter then consumes those instructions. Bytecode is often called an intermediate representation of Python code because it expresses the source code that you wrote in a way that the interpreter can understand. This is analogous to the way that assembly language is an intermediate representation between C code and a piece of hardware. Now, an intermediate representation like this adds a layer of complexity to your execution model, so there is a cost to it in that sense. But the advantage is that all this work, the lexing, parsing, and compiling, only has to be done once for each code object instead of every time you need that code object later. So our goal today is a bytecode interpreter. So why would you write an interpreter? CPython is pretty good, and rewriting it, particularly using the strategy that we took, which is to rewrite it in Python, is not going to make it faster or better in most ways. So for Ned Batchelder, you may know him as the author of coverage.py, which is a test coverage framework that a lot of folks use. And this is a really trivial example of a line of code where line-level coverage can be misleading. You may have written a test that tests A but not B, and so you could have a bug in your program here, and line-level coverage wouldn't catch that. So the original goal of Byterun was to investigate whether bytecode level coverage would be an interesting thing to pursue. And one of the lessons from working on this project is that it's extremely fiddly, and we have not ended up pursuing that. I was in this project mostly just as an intellectual exercise. I think it's very fun and interesting. So the next question is, why write a Python interpreter in Python, and particularly doing it in this relatively naive way that we were doing as opposed to something more sophisticated like PyPy has taken? The obvious disadvantage is speed. This is not going to be a functional interpreter in any interesting way. But since the goal is to understand the real CPython interpreter, we don't actually care about speed of execution. So we're writing in a high-level language, Python, that we know how to read and write very effectively, and so we end up with this product that is very easily understandable. The other significant advantage is because we implemented an interpreter in Python, we didn't have to implement the object system. We just say, okay, when you get to an object, fall back to the real object system already there in Python. And so the interpreter can do sort of just the bytecode stage of things. So this is an example of a test in Byterun. The idea here is that we run the code under the real Python interpreter, and then again under Byterun, and we make sure that the same thing happens. So we capture standard out, we capture exception state, we compare what got printed, and we compare the exceptions, and so on. Comparing Byterun to a reference implementation is a really great way to do quick debugging. And this is, in fact, the same strategy that's used for many new implementations of Python, like Piston, which is being worked on at Dropbox. So this is the basic structure of a test in Byterun, and this one passes. So we have implemented for loops in a way that works correctly. And in fact, as of about a year and a half ago, most things worked correctly. We could do loops, we could do function calls, we could do exception handling, we could do context managers, decorators, generators, and so on. We had one problem that was stumping us. In particular, we got errors on nested generators. We got a really weird error, too. We would try to run this code, which should work just fine, and we'd get a type error that we were trying to multiply two none objects, which is obviously not going to succeed, and also not at all clear where that's coming from in this code. So I'm going to talk a little bit about the structure of Byterun, which it mirrors the structure of the real CPython interpreter, to uncover this bug. And it's kind of amazing how well this worked, considering how wrong we were about the structure. And just to be clear, everything that I'm going to describe here is the correct structure, and then I'll reveal what our misunderstanding was towards the end. So to make this concrete, let's start with a very minimal interpreter. This interpreter understands just 3 instructions. Here they are: load a value, add 2 values, and print the answer. All the code it can execute consists of these 3 instructions in different combinations. Since we're not concerned at all today about the lexer or parser or compiler, we don't actually care how you got these instructions. You could imagine that you wrote 7 + 5 in sort of a Python-y syntax, and some friendly compiler somewhere generated the 4 instructions that you see at the bottom. Or if you had a different compiler, you could write Lisp syntax and get these 4 instructions at the bottom. Today, we don't care. The interpreter just cares that there is a well-formed arrangement of these 3 instructions, and this is one that is well-formed. So now let's talk about what we want these instructions to do. The Python interpreter is a stack machine, as I mentioned earlier. So it's going to manipulate stacks to add 2 numbers. It'll manipulate stacks to do everything. Now, when you hear about stacks, you're probably thinking first of the call stack. That is not the stack that we're talking about right now. So hold that thought. We will come back to the call stack in a minute. But for now, ignore it completely. So we have some stack that can hold data. When the interpreter begins, the stack is empty. It executes the first instruction, which pushes the first number onto the stack, that's 7. And then it pushes the second number onto the stack, that's 5. And then it adds them together, pushes the result onto the stack, that's 12. And then with print answer, we'll pop the result off the stack and print it. So the manipulation here is load value is responsible for getting values onto the stack. Add 2 values is responsible for popping them off and adding, and print answer consumes whatever's on the stack and prints it. You may be wondering at this point why instructions other than add 2 values are necessary at all. And admittedly, for the case where we just add 2 values, it is slightly contrived. But this creates a strong framework that we can use to add a lot of complexity. So just with the interpreter instructions we've designed so far, we can add 3 values, or any number of values, if we have this well-formed set of instructions. And the stack provides a really clean way to track the interpreter's state, and it will support a lot more complexity as we go on. So the next question is, where do these numbers come from? In our example of the instructions, it just says load value, but it doesn't say what value to load. So we have to tell the interpreter that. So let's expand our instructions a little bit. Instead of having just a list of instructions, we'll have this dictionary, which we'll call what to execute. There are 2 pieces, the instructions themselves, and then the numbers, which we'll also need. And we also need to link each number to the correct instruction. So load value the first time should load the first number, and then the second time will load the second number. In Python, what I'm calling instructions here is the bytecode itself, and the whole what to execute object is analogous to the code object. So why not just put the numbers directly into the instructions? So imagine if we were adding together strings instead of numbers. We might not know how long those strings are, and we might want to pack the instructions in a way where the length is already predetermined. The other advantage to this design is if we're adding 7 plus 7 instead of 7 plus 5, we only need one copy of the number 7 in the code object. This comes in handy in a lot of places. OK, so let's start writing our interpreter itself. We know that our interpreter needs a stack. Right now, that's almost the only thing that we need in our interpreter. And we need to implement the instructions so the interpreter knows what to do when it hits that instruction. So here we have 3 functions that are named analogous to the instructions: value loader for load value, answer printer for print answer, and toValue adder for adding the instructions, or for adding the values. And you'll notice that each of these interact with the stack in the way that we just outlined, that value loader pushes something onto the stack, and toValue adder pops something off, and so on. So we need just one more piece, a way to actually make the thing go. So here we have a method called runCode, which takes that what to execute object and does what it says in it. So the first thing we do is unpack into instructions and numbers, just for clarity and readability. Then we loop over the instruction. We process the argument to that instruction, if there is any, which there might not be. And then we call the corresponding method on the interpreter object. And we just do that with an if statement. We have a method defined for each instruction. And so we say, if we're looking at the load value instruction, then call the value loader function with the correct argument. So this interpreter is quite limited, but this process is almost exactly how the real Python interpreter adds 2 numbers. And there are a couple of things that we can notice just from this small example. The first one is that some instructions do need arguments. In real Python bytecode, it's about half of the instructions that need arguments and half do not. The second thing to notice is that the arguments to the instruction are packed in with the bytecode, where we had load value 0. That's basically the way the bytecode is structured as well. And we can notice that the arguments to the instructions are different than the arguments to the function being called. So for load value, we need to go look up what the correct argument is, and then pass that number, not the index into the numbers list that we saw earlier, but the actual number at that point into the value loader function. And finally, notice that the add 2 values did not require any arguments. So the instruction itself just says, take whatever is on the top of the stack and add it together. The top 2 things on the stack, add that together. This is the defining feature of a stack-based interpreter, is that we will be manipulating the stack, and anytime we're doing a calculation, basically the values have been on the stack at some point. OK, so let's now graduate to real Python bytecode. As I mentioned, these instruction sets in Python are called bytecode, and the overall object is called the code object. One great thing about Python is it exposes a ton of internal implementation details in the REPL, so it's really easy to poke around and explore and see what's going on. And so it won't be too hard for us to do. So here's a function that we can use to explore. It's simple. It's called mod. It takes 2 arguments, calculates the modulus of one against the other, and then returns the result. So we can get a handle on the function object, which is mod, on the mod function's code object, which is funcCode, and then we can get a handle on the bytecode, which is stored under cocode. And again, bytecode is a subset, not the same thing as the code object. OK, so let's take a look at this. So just printing this doesn't feel very enlightening. But there is, in fact, one thing that we can learn just from doing this, and that is that bytecode is a series of bytes. It's a series of numbers between 0 and 255. And it looks a little funny in the terminal because some of them are printable and some of them are not. But we already know something about bytes just from that. We can make this slightly more intelligible by converting to ordinals. And this really shows us that these are numbers between 0 and 255. But it's still not exactly readable. So luckily for us, there's a tool that we can use in the standard library to make this intelligible. We can use dis, the bytecode disassembler. And in general, you want a disassembler when you have some set of instructions that are intended for a machine, and you want to make them readable for humans. So assembly language is a case where you would use a disassembler very often. An intermediate representation like bytecode is another example. I can't think of a reason why you would want to use dis in production. In fact, dis doesn't even return this output. It just prints it. This is really intended for our eyes and not for any machine consumption. OK, so we've run our function through the disassembler. We get this output. I've got this annotated slightly just below the call. The left-hand column is the line number in the original source code. So our code was 2 lines, and this is line 2 and 3 from the REPL. The second column is the index into the bytecode. So this is telling us that at position 0 is load fast, at position 7 is store fast, and so on. The third column is the instruction, is the byte mapped to a human-readable instruction name. So 124 becomes load fast, and 22 becomes binary mod, which is much friendlier for us to read as humans. The fourth column is the argument to the instruction. And notice again here that binary modulo does not take any arguments. And the first time that I saw this, I was really surprised and confused, because I would assume that a binary function is one that takes 2 arguments. That seems definitionally true. But in bytecode, those arguments are already going to be on the stack. So the instruction itself does not require arguments. And then the fifth column is a hint from elsewhere on the code object about what that argument actually means. So we can tell that the first time you do load fast, you're getting A, and the second time you're getting B, and so on. OK, so what happens in the interpreter when we call this function? Well, it's just like our miniature example before. The Python interpreter pushes the value of A onto the stack, that's 7. It pushes the value of B onto the stack, that's 5. And then it calculates binary mod of one against the other, gets 2, and pushes that result onto the stack. And then the answer gets stored by the store fast instruction, which means that the name answer in our example will be bound to the number 2. So now what? We've completed this first line of code here, the answer equals A mod B, and we're down to line 3. We know what load fast does. Here in position 10, second line up from the bottom. That pushes a value onto stack. And then there's return value, which presumably is related to this return statement. But in our current mental model of the interpreter, there's nowhere to return to. So at this moment, I'd like you to remember the call stack that I asked you to forget earlier, and zoom out a level. So the call stack now is modeled top to bottom, and the data stack, which is the stack we've been looking at so far, is going left to right. The stack that the interpreter is using for calculations, I don't know if data stack is the common terminology, but certainly it is a stack that contains data, so that's the term I'll be using today. Meanwhile, the call stack is made up of frames. You have 1 frame on the call stack for each level of your code. And this is something that you're probably viscerally really familiar with, because you see it all the time in tracebacks. So your traceback, when it says most recent call last, and then has several levels, each one of those levels corresponds to a frame. So 1 frame per function call, 1 frame for a module, and so on. And each frame has its own data stack, and then it also has another stack of blocks, which I'm not going to talk about today. So this is what the interpreter looks like in the middle of executing mod, which is right before the binary modulo happens. There's 2 frames on the stack, 1 for the main scope, and 1 for our function mod. And when return value is executed, what that's doing is it tells the interpreter to pass a value from 1 frame to another. Now, return value is one of only 2 ways to accomplish that. The other way is with yield. And I want to emphasize that there's 1 frame on the call stack for each function call, not for each function object or something else like that. And again, picture yourself maybe accidentally hitting the recursion limit where you get a traceback that is 500 frames long, even though it's all the same function being called. So if we had a recursive call like this factorial calculation, and it'll start out looking like this. I'm not showing the bytecode here, but at this point we're in the middle of the call to fact of 3, and I'm about to calculate 3 minus 1. So we do that, we get the answer 2. At this point, we have the function object factorial on the previous frame's data stack. I know this is a little bit weird. Calling a function consumes a function object off of the stack this way. And when it's actually called, it creates a new frame for the deeper recursive call. So then the interpreter is loading up n again, which is now 2, and pushing that onto the stack. Notice also that there's a value left on the data stack in the previous frame. So that's the n in the result that is waiting for fact of n minus 1 to finish executing so we can come back to it. We'll need it there to multiply when this call stack is unwinding. Now, skipping ahead a little bit, we'll eventually hit the base case, and we'll start unwinding. So the 1 gets returned from the top frame down to the next one down, and multiplied again, gets 6, and pass that back to the calling frame. So these are the basic pieces that we need to implement a Python interpreter, our own virtual machine. We need some way to create frames. We need to provide a data stack for that frame and also a block stack. And we need to define a way to run the frames. And to run the frames, we need to define the correct operations for each instruction that we may hit, just as we did for our toy interpreter at the beginning. The only difference is that now there are a lot more instructions. I'm omitting a couple of other necessary ingredients, like tracking the exception state and tracking namespaces and scopes and that sort of thing. If there's time, I can talk about that in Q&A. So we have a lot more instructions to define for a real Python interpreter. And of course, the complexity of each instruction is also greater. So we need to write the operations that the interpreter should perform for each of these instructions for this to be able to execute. So what should those be? Well, the good news is we're not starting from scratch. We have CPython, the reference implementation, and we can look at how it is implemented in the reference implementation in the actual CPython interpreter and get guidance. And the main loop of the Python interpreter is in the file ceval.c. I saw on Twitter earlier that in Carol Willing's talk, David Murray said that the way to get into the CPython codebase is to start in ceval.c, be confused, and then expand from there. So today we're going to do at least 2 of those steps and hopefully 3. So in our toy interpreter, can you see this okay in the back? In our toy interpreter, we had a big if statement, or what would have been a big if statement, saying, if the instruction is this, then do this. If the instruction is this, then do this. CPython is implemented in the same way, and the meat of ceval.c is a 1,500-line switch statement over the opcodes. And this is it. And I love this because it feels like such an obvious implementation in some ways. Like you can imagine, sitting somewhere in the Netherlands in 1989 and saying, okay, we have these instructions, and each of them maps to a set of things that need to be done, and we're writing C, so how should we do that? Well, how about a giant switch statement? And that's exactly how it works. In fact, a 1,500-line switch statement is so large, or sorry, let's come back to this. So a 1,500-line switch statement is so large that it breaks some C compilers. And there is a macro that you can turn on if it breaks your compiler. So you can turn the giant switch statement into 2 switch statements that are only 750 lines each. So the interpreter is basically taking each instruction and then using a switch statement to look up the correct things to do and then doing those things and then moving to the next instruction. In Python 3 and up, this is no longer literally a switch. It is computed go-tos instead, but the idea remains quite similar. Okay, so these were the instructions that we needed to know how to implement for our Python interpreter. So let's take a look at that implementation. So here's load fast. This is the first instruction defined. It's the most common instruction in most Python code bases. And the C is pretty readable here. You can see that we run this macro getLocal and store the value. And if anything goes wrong, then we throw a unbound local error. Hands up if you've thrown an unbound local error before. Right, so this happens when you try to load a local variable and something happens. But in the meantime, if something has not failed, then we push the result onto the stack and we move on to the next opcode. So here is the code that raises that error. That's the only place in the CPython codebase where that's raised, I think. That's pretty cool that we can just find that right there. And here's binary modulo. So we pop 2 things off the stack. In practice, it's not quite that, but it's close enough. We do some stuff, we calculate the remainder, and then we push the result back onto the stack. Cool. So I've described the structure of CPython and by extension the structure of Byterun using all of the information that we know today. But up until about a year ago, we had one thing really wrong. And in particular, we only had 1 data stack for the entire interpreter instead of 1 data stack per frame. And what's really interesting is how much is possible despite making that error. So in this case, nesting the generators pauses and resumes the frame of G several times, and it has to do some work in between pausing and resuming. And so that work is also manipulating the stack that should belong to the separate frame, but instead was in the wrong place. And the none appeared, and we tried to multiply it because resuming a generator pushes none onto the stack, and then the generator frame knows how to consume that appropriately. So understanding the correct structure here, that in fact there is 1 data stack for every frame, gives us the ability to pause and resume frames, which is what we need for generators. And by contrast, if the Python interpreter were implemented with only 1 data stack, the only feature that you would lose is generators. So in the last couple of minutes here before Q&A, I want to talk a little bit about how Python is dynamic. And one thing, you hear this a lot, like, oh, Python is a dynamic language, it has dynamic typing. And if you listen to Guido's keynote, or I guess it's the closing talk tomorrow about type hints, you're going to hear something about the future of types in Python. I think a lot of folks, particularly those who are still in Python 2, which is most of us, unfortunately, are not super familiar with what's going on here. But with the context we've just built up about the interpreter, we can take a look at one of the problems that this is trying to solve. So one thing that dynamic means is that a lot is happening at runtime. And another way of putting this is that not a lot is happening at compile time. And the interpreter has a lot of work to do. So let's look at actually calling this function mod. It's pretty obvious what's going on here. We call mod on 15 and 4, and we get the result 3. Any guesses for what will happen when we call the function like this? Right, well, we get PyCon returned. So this might look really weird to you, but you've almost certainly seen it before. You've seen it as string formatting. So doing string formatting with a modulo like this is just invoking binary modulo on the arguments. So this is the bytecode for this function, and this is always the bytecode for this function. The advantage is that we build this once and we reuse it again and again. So no matter what arguments are passed to it, we're going to call binary modulo on whatever the top 2 items on the stack are. And they may be 2 integers, or they may be a tuple and a string, or 2 strings. The compiler does not know, and the compiler does not care. It's up to the interpreter to do the right thing. So I went by this kind of fast on purpose earlier. But one thing that you notice here is that there is an if statement saying if v is a string, then dispatch to string formatting. This kind of looks like it's type checking. It's actually even worse than that. The type checking here is an optimization. Because, of course, we could pass anything to our modulo function. It doesn't have to be either a string or a number. And so this number remainder is responsible for eventually doing dispatch on whatever the object is. So this gets even worse than this, because this is Python, right? So we can define our own types, and we can define what different operations mean on those types. So we could write an object that has a side-effecting mod function. So here I've written mod that prints something when you mod one object against another. I don't know why you'd want to do this, but you could. And it is strictly up to the interpreter to resolve what it means to binary modulo on our object. So the compiler's ignorance is really deep. There's this great paper by Russell Power and Alex Rubinstein called How Fast Can We Make Interpreted Python? And their conclusion from the strategies that they tried was that it's very challenging. And the quote here is, in the general absence of type information, almost every instruction must be treated as invoke arbitrary method. So given that the compiler knows so little, without running the code, we can't really optimize it. We don't know what instructions we can take out. We can't really reason about its correctness. All those things are very hard to do because the language is so dynamic. But notice the caveat here, in the general absence of type information. And so one way to solve this problem is to say, fine, let's add type information. And there's a lot of nuance to how exactly you do that and how to make that not break for people who are not interested in those sorts of things. But in the next version of Python, this is basically what's happening. You can add optional type information to your Python, and the static analysis tools will be more robust because of it. It opens up a lot of interesting possibilities that just aren't there when everything is so dynamic. Okay, so I'll put up these links a little bit later. The couple of great blogs, Aknin and Eli Bendersky have great articles about the interpreter and internals and the go-to statements and so on. In the meantime, I will go ahead and take some questions.
Thank you, Allison. So if anyone has any questions, please come to the center of the room and stand in front of the mic so that the video can pick you up.
Great talk, thanks. Is there any possibility of doing like dynamic optimizations? Like
Sorry, doing what sort of optimizations?
I'm not very aware of the internals of the Python interpreter, but can you do like example in the Java JVM, it will start rewriting things as it's running? Does Python also do that, or? Yeah,
so Python does a couple of optimizations in the couple of places where it can. So one of the optimizations is constant folding. For example, if you have a function that says return 3 plus 2, the Python compiler will turn that into return 5.
Okay.
Because Python is so dynamic, there's very few cases where, under the current structure, you can optimize. And the source in this is fairly readable. I had a blog post about constant folding and the way it messes up the bytecode level coverage because the bytecode ends up changing out from under you. But it happens a little bit, but it's pretty limited because of the structure.
Okay, thank you.
Hi. I'm researching on interpreters and JIT VMs and small VMs. So I'm not that very familiar with CPython's interpreter, but I just wanted to know that is it a real simple switch case, or is there small optimizations like threaded dispatch or dynamic threaded dispatches? So there are multiple ways. So is it just a simple switch case, or is it something else? And is there a possibility to JIT this code to optimize it just like PyPy does?
Yeah, so to the first question, is this a literal switch statement? Are there optimizations? Yes to both. So the code is like literally, case, load fast, case, so on, in Python 2. And there are a couple of optimizations where, in particular, there are pairs of bytes that often follow each other. So if you have like a get iter, there's probably a for iter right after it. And the interpreter is smart enough to say, okay, check first at this particular byte that usually follows this one we know about. So that's one optimization. And there are also a number of others. There's some things that only happen, some work has to be done in between each instruction, some work is done every 100 instructions, those sorts of things. In terms of whether this structure can be JITted, I don't know a whole lot about the way that PyPy is implemented. And I think that PyPy is sort of an existence proof that this cannot. Like you wouldn't have to go that direction and solve the problem with a completely new interpreter and a new set of bytecode if this were amenable to sort of incremental change.
Okay, thank you.
I'm sorry, this may be a stupid question, but do the type annotations have anything to do with JIT compiling?
No, I think it's the short answer to that. The type annotations are designed to help static analysis. So without running the code, what can we say about it now? Doing JIT compilation, I think it's more or less a separate problem, yeah.
You alluded to the block stack a few times. Can
Yeah.
you explain what that actually is and what it means?
Yeah, in short, the block stack is keeping track of state in a different way. So the classic example is for an iterator. If you're on the top instruction of an iterator, you're either going to step to the next instruction if you're in the body of the for loop, or if you're done, you're going to jump out of the for loop. And so the block stack is responsible for keeping track of that. It's used for looping and exception handling, and I think that's pretty much it. It's just like another way of managing state.
Hi. I noticed in your example of modulo, you assigned like a modulo b to answer and then return answer.
Uh-huh.
If you just did like return a modulo b, does Python like create a variable for that stack?
It would not create a variable. Yeah, so you're talking about, so what we'd see in that case is you would have binary modulo and then immediately return value, because all the return value needs is the result on the stack. So this is just for readability, yeah. And the interesting thing there is that my binding a name answer to this is what makes Python say, okay, pull this off the stack and like put it into the environment, and then immediately retrieve it from the environment and return it. So this is something that I didn't get into too much about, the way that the frame also has to manage the namespace. This is what is currently in the local scope. And that gets modified as you do things like store fast and load.
Thank you.
Thank you very much, Allison.